Hi everyone, welcome back to my YouTube channel lecture series on microcontroller and ARM processor. In this video, I am going to explain a round-robin scheduling algorithm. It is the most popular algorithm which is used in operating system. A round-robin algorithm is a preemptive process scheduling algorithm. Each process is provided a fixed time to execute. It is called as a time quantum or a time slice. Look at this problem. I have taken 5 processes which are represented as P1, P2, P3, P4, P5. For each and every process, we have arrival time and the burst time. Burst time in the sense the P1 process has to complete its execution with 8 units of time period for P1 process. Similarly, for other process, I have a burst time. So in this problem, I have taken a time quantum value of 3, which means the CPU has to execute each and every process with the maximum time period or time quantum of 3 units. So before you are assigning the process into the CPU in a cyclic way, the processor has to wait in the ready queue. From the ready queue, you can move the process one by one to the CPU for scheduling. So this algorithm can be called as a round robin algorithm. So each and every process will be moved to the CPU in a cyclic way. Now we'll see how to schedule the process in the CPU and how the process is moved into the ready queue. So first what you have to do is you can just see the arrival time of each and every process and see which process is quickly approaching the ready queue based on the arrival time. So the P1 process arrival time is 0. So the P1 process will arrive the ready queue. So from ready queue, I can move the P1 process to the CPU for scheduling. As we already mentioned, the CPU will execute a maximum of 3 units of time for each and every process. So the P1 process burst time is given as 8, but the CPU will execute only 3 units of time. So 8 minus 3 is 5. There are 5 more units left out to complete the execution of P1 process. When the CPU is executing the P1 process, you have to check if any other process arrived in the ready queue. So based on the arrival time, you can check from 0 to 3. You can check any process waiting in the ready queue. So the P3 process arrival time is 1. This one is within the strings 0 to 3. So you can put the P3 process in the ready queue. So first you have to check if any other process is waiting in the ready queue when the CPU is executing the current process. Okay, next you can preemptive this P1 process back to the ready queue. So when the CPU is executing the P3 process, the P1 process should be preempted. So the P1 process have to put back to the ready queue because the P1 process has 5 more units to complete the execution. So I can call the P3 process to the CPU for scheduling, and the P3 process will execute 3 units of time, and the P1 process is preempted and the value is taken as 5 for P1 process. There are 5 more units to complete the execution of P1 process. Now what CPU is doing? The CPU is executing the current process, that is the P3 process, and also you have to check if any other process is waiting in the ready queue from 3 to 6. The arrival time 3 to 6, you can check any other process waiting in the ready queue. If you look at this problem, there are 2 processes waiting in the ready queue, the process P2 and P4. This 2 arrival time is within this time period 3 to 6. So you can put the P2 process and P4 process which has arrived in the ready queue, and you can preemptive this P3 process. Okay, so what you have to do next, you call the P3 process to the CPU. You can put the P1 process and it will execute a 3 units of time. While the CPU is executing this P1 process, the P3 process has to be preempted. Okay, so the P3 process again put into the ready queue because the P3 process executed only 3 units of time and you have 4 more units to complete the execution of P3 process. So 7 minus 3, you have 4 more units to complete the execution of P3 process. Now I can call the P2 process. So before calling this P2 process to the CPU for scheduling, you have to check if any other process is waiting in the ready queue from 6 to 9. Okay, if you look at this problem, you have arrival time for P5 process 8. So this is within this range 6 to 9. So you can put this P5 process in the ready queue. So the P5 process arrived in the ready queue when the CPU is executing the P1 process. Now what you can do, you can call next P2 process to the CPU for scheduling, and it will execute only 2 minutes of time, because the burst time for P2 processors given this problem is only 2 units. So the CPU will execute only 2 minutes of time from 9 to 11. Okay, and P1 process have few more units left out, which are 5 minus 3, it is 2 units. Okay, so first time it executed 3 units, so 8 minus 3 is 5. Again it is executing 3 units, so 5 minus 3 is 2. So here we are putting this P1 process back to the ready queue, so it has 2 more units to complete the execution. When the P2 process is executing, the CPU is executing the P2 process. So if you look at this problem, the P2 process first time is 2, and the CPU is also completed the execution with 2 units of time, and you can confirm that the P2 process will not participate in the scheduling process further, because the time of the unit of time is over. The 2 units it already executed, so it will not participate, or it will not come into the scheduling process further. Okay, so after P2 you can call a P4 process to the CPU for scheduling. A P4 process total burst time is 3, so the CPU will execute a 3 unit of time from 11 to 14. So here also the P4 process completed its execution, because it has a maximum burst time of 3, and you can say that the P4 process will not participate in the scheduling process further. So after which you can call the P3 process. The P3 process will execute 3 units of time. So already you have 4 more units left out in the P3 process. So here the P3 process execute only 3 units of time. So 4 minus 3, it is 1. So we have 1 more unit left out in the P3 process to complete the execution. Okay. Now what you can do, we can call the P5 process to the CPU. The P5 process total burst time is 5, but the CPU execute only 3 units of time. So 5 minus 3 is 2. So there are 2 more units to complete the execution of P5 process. Okay. So before you are calling the next process to the CPU, you can check the P3 process left out time is 1 unit. So you can just preempt this P3 process, and you can move this P3 process back to the ready queue, because the P3 process still you have 1 more unit to complete the execution. So I am preempting this P3 process and putting into the ready queue. Now the P5 process is executing for maximum time unit of 3 minutes. Okay. After P5 you can call the P1 process. The P1 process, here the left out time is only 2 units. Okay, so the CPU will execute only 2 units of time to complete the execution of P1 process from 20 to 22. After P1 process, you can call the next process from the ready queue to the CPU. P3 process will be executed by the CPU. The P3 process have only 1 unit of time is left out. Okay, so it will execute only 1 unit of time from 22 to 23. So P3 process execute 1 unit of time from 22 to 23. Next you can call the P5 process to the CPU for scheduling, and you have 2 units to complete the execution of P5 process. So the CPU will execute only 2 units of P5 process, and it will complete the scheduling process at the value of 25. 23 plus 2 is 25. So it will complete the execution of P5 process at the value of 25. So using this data, we will see how to fill the completion time, turnaround time, wait time, and response time. If you take the completion time for P1 process, you can see in the gain chart. Okay, the P1 process executed from 0 to 3, then 6 to 9, and finally it executed from 20 to 22. So the completion time in the sense how much time each process will be taken to complete the execution. Okay, so the P1 process completed the execution at the value of 22. Similarly, for P2 process completed its execution at the value of 11, and P3 process completed its execution at the value of 23, and P4 process completed the execution time at the value of 14. P4 process is 14, and P5 process completed time is 25. So based on this, you can fill up this completion time. So next you have to find out the turnaround time. The turnaround time is nothing but completion time minus arrival time. The completion time is 22 minus the arrival time given in this problem is 0. So 22 minus 0 is 22. Then 11 minus 5 is 6. 23 minus 1 is 22. 14 minus 6 is 8. Then 25 minus 8 is 17. So after finding the turnaround time, you can find out the wait time for each and every process. The wait time is a turnaround time minus a burst time given in the problem. So the turnaround time is already calculated as 22. 22 minus 8 is 14 and 6 minus 2 is 4. 22 minus 7 is 15. 8 minus 3 is 5 and 17 minus 5 is 12. Now we can fill up the wait time. So after this you can find out what is the response time. The response time is nothing but the arrival time of each and every process in the Gantt chart minus the arrival time given in the problem. So the response time for the first processes, the P1 is response time is 0. So 0 minus 0 is 0. Then for second process the arrival time is 9. Second process the arrival time is 9, but the problem it is given as 5. Okay, so 9 minus 5 you will get 4. Similarly you can fill up the remaining process arrival response time. So after which you can calculate the average of turnaround time, wait time and response time. So if you take the average of the turnaround time, you will get 15 milliseconds, and for wait time you will get 10 milliseconds, and if you take the average of the response time you will get 4 milliseconds. So this is a round robin scheduling algorithm. If you see the advantage of using this algorithm, every processor is allocated in a cyclic way. So the round robin is a cyclic in nature, there is no starvation. But if you take the disadvantage of using this kind of algorithm, if you take the time quantum value of less number, if you take example, I am keeping the time quantum value is 1. Okay, so each and every time the CPU will execute only 1 unit of time for each and every process. For example, there are 5 processes in this case, and I am fixing the time quantum of 1. So the P1 process will execute maximum 1 unit of time, and the remaining process also execute a maximum 1 unit of time. So if you take time quantum as 1, the context of switching from processor 1 to processor 3 and then processor 3 to processor 1, like that it keep on goes, and it will lower the CPU efficiency. So by setting this quantum as too short, that will lower the CPU efficiency. It will increase the context of switching from one process to the another process. So that is a drawback of using this round robin scheduling algorithm. And one more disadvantage is that if you increase the time quantum number, say for example I am just keeping this time quantum into some 10 or 12, okay, that may cause the poor response to a short process. That is also another drawback of using a round robin scheduling algorithm. Thank you for watching.